Welcome to Networking Fundamentals for IT Helpdesk. This lesson will examine the essential networking concepts that every IT helpdesk professional should know. From understanding the basics of routers, switches, and wireless access points, this lesson will give you a solid foundation to troubleshoot and manage network issues effectively. Whether you are new to IT or looking to improve your networking skills, this video will equip you with the knowledge needed to keep your organization's network running smoothly. This session will cover the basics of computer networking, including key concepts and terminology. You'll learn about essential networking devices like routers, switches, and firewalls, and their roles in network infrastructure. We'll also dive into network maintenance and troubleshooting techniques to equip you with the skills to resolve common network issues efficiently. Finally, we'll discuss how mastering these networking skills can help you advance your IT helpdesk career, providing opportunities for more advanced roles and responsibilities. In this first section, you'll be introduced to the foundational concepts that underpin all computer networks. You'll learn about the core principles of data transmission, the importance of IP addressing and subnetting, and the various types of networks. By understanding these essential elements, you'll be better equipped to troubleshoot and manage network issues, ensuring efficient and secure communication within your organization. This session will provide the critical knowledge you need to excel as an IT helpdesk professional. Computer networks, the backbone of modern communication and data exchange, are fascinating systems that enable devices to connect and share resources efficiently. In this context, we will examine these intricate networks' key concepts and components. 1. Definition of a computer network. A computer network is a collection of interconnected devices, computers, servers, printers, etc., that communicate with each other to share data and resources. 2. Types of networks. Local area network. This network type covers a small geographic area, such as a home, office, or building. Wide area network spans large geographic areas such as cities, countries, or continents. Metropolitan area network covers a city or a large campus. Personal area network connects devices like Bluetooth and USB connections within a personal workspace. Free network topologies. Bus topology. All devices share a common communication line. It is simple, but can be slow and unreliable if the main cable fails. Star topology. All devices are connected to a central hub. More reliable and easier to manage. Ring topology. Devices are connected circularly. Data travels in one direction, reducing collision chances. Mesh topology. Every device is connected to every other device. Highly reliable but expensive and complex. 4. Network devices. Router connects different networks and directs data between them. Switch connects devices within a network and uses MAC addresses to forward data to the correct device. Hub, a basic device that connects multiple devices in a network, but unlike a switch, it sends data to all devices. Modem converts digital data to analog for transmission over telephone lines and vice versa. 5. Network protocols. TCP/IP, a transmission control protocol, Internet protocol, fundamental protocol suite for the Internet, ensuring data is sent and received correctly. HTTP and HTTPS, used for web communication. FTP, file transfer protocol, used for transferring files between computers. SMTP, simple mail transfer protocol, used for sending emails. DNS, domain name system, translates domain names to IP addresses. 6. IP addressing. IPv4 uses a 32-bit address scheme, allowing for about 4.3 billion unique addresses. IPv6 uses a 128-bit address scheme, allowing for a virtually unlimited number of unique addresses. 7. Network security. Firewall filters incoming and outgoing traffic to prevent unauthorized access. Encryption secures data by converting it into a code authorized parties can only decipher. Antivirus software detects and removes malicious software. 8. Common networking issues. Latency, delay in data transmission. Bandwidth, the maximum rate of data transfer across a network. Packet loss, data packets fail to reach their destination. Jitter, variability in packet arrival times. Grasping these fundamental concepts is beneficial and essential for effectively designing, managing, and troubleshooting computer networks. This knowledge is the key to resolving connectivity issues, ensuring network security, and optimizing network performance, particularly for IT helpdesk roles. Network architecture and design are crucial for ensuring that a computer network meets the needs of its users and operates efficiently and securely. Here, we'll cover the basic principles and components of designing and architecting networks to include network architectural models. These models are not just theoretical constructs, but practical tools that provide a framework for designing and understanding a network structure and functioning. The most prominent models are the OSI Open Systems Interconnection model and the TCP/IP Transmission Control Protocol Internet Protocol model. These models play a crucial role in ensuring network efficiency and security by standardizing network communication and aiding in troubleshooting. OSI model, Open Systems Interconnection. The OSI model is a conceptual framework for understanding and implementing network communications. It divides the communication process into 7 layers, each with specific functions. Layer 1, Physical, deals with the physical connection between devices, including cables and switches. Layer 2, Data Link, manages node-to-node data transfer and error detection. Layer 3, Network. This layer handles the routing of data packets between devices on different networks, for example, IP addresses. Layer 4, Transport, ensures complete data transfer with protocols like TCP and UDP. Layer 5, Session, manages sessions or connections between applications. Layer 6, Presentation, translates data between the application and network formats. Layer 7, Application, interfaces directly with the end user and applications. TCP/IP model. The TCP/IP model is more streamlined and practical and can be used for network implementations. It simplifies the OSI model into 4 layers that correspond directly to the functionality of Internet communications. Network interface corresponds to the OSI's physical and data link layers. Internet corresponds to the OSI's network layer. Transport corresponds to the OSI's transport layer. Application encompasses the OSI's session, presentation, and application layers. Components of network design. Each component is crucial in designing a robust, efficient, and secure computer network. Understanding these components is essential for network engineers and IT professionals to build, maintain, and troubleshoot networks effectively. Routers and switches, devices that forward data packets between networks or devices within a network. Firewalls protect the network by controlling incoming and outgoing traffic based on security rules. Access points provide wireless connectivity to the network. Cabling, physical medium through which data travels, including copper cables and fiber optics. Servers provide resources and services to network users. Network design principles are fundamental guidelines and best practices that network architects follow to create efficient, scalable, and secure networks. Here are some key network design principles. Scalability. The network should support growth in the number of devices and users. Reliability. The network should provide consistent and dependable performance. Security. Measures should be in place to protect data and resources from unauthorized access. Performance. To meet user needs, the network should have minimal latency and high throughput. Maintainability. The network should be easy to manage and troubleshoot. By adhering to these network design principles, architects can create robust, efficient, and secure networks that meet the needs of organizations now and in the future. Introduction to networking technologies involves understanding the fundamental concepts and components that enable communication between devices and systems. Here's a breakdown. 1. Networking basics. This is where your networking journey begins. Understanding these basics is crucial as they lay the foundation for all the advanced concepts you'll encounter later. Definition of a network: a collection of computers, servers, mainframes, network devices, routers, switches, and other devices connected to shared data. Types of networks: local area network, wide area network, wireless local area network, metropolitan area network, etc. 2. Networking devices. Router connects multiple networks, typically operating at the OSI model's network layer, a layer 3. Switch connects devices within a network and operates at the data link layer, a layer 2. Hub, a basic networking device that connects multiple Ethernet devices and operates on layer 1. Free, network topologies, bus topology, all devices share a single communication line. Star topology, all devices are connected to a central hub or switch. Mesh topology, devices are interconnected with many redundant paths between them. 4. Network protocols, TCP/IP, a transmission control protocol, Internet protocol, fundamental protocol for the Internet. UDP, user datagram protocol, this is a connectionless protocol for sending datagrams. HTTP and HTTPS, hypertext transfer protocol and hypertext transfer protocol, secure for web browsing. FTP, file transfer protocol, used for transferring files over a TCP/IP network. 5. IP addressing, IPv4, 32-bit address format. IPv6, 128-bit address format. 4. Network security, firewalls, control incoming and outgoing network traffic. Encryption, secures data to prevent unauthorized access. VPN, a virtual private network, securely extends a private network across a public network. 5. Network services, DNS, domain name system, translates domain names to IP addresses. DHCP, dynamic host configuration protocol, automatically assigns IP addresses to devices on a network. NAT, network address translation, translates private IP addresses to public IP addresses. Understanding these fundamentals will provide a solid foundation for troubleshooting and managing networks effectively. In networking, some essential devices commonly used are: router, connects two or more discontiguous networks to the Internet, typically a local network. Switch, this device connects devices within a single local area network and manages data traffic between them. Hub, this is similar to a switch but less efficient, as it broadcasts data to all devices in a network segment. Access point, AP, allows wireless devices to connect to a wired network using Wi-Fi. Firewall, controls incoming and outgoing network traffic based on predetermined security rules. Modem, converts digital data from a computer to analog for transmission over telephone lines or vice versa. Network interface card, a hardware component that connects devices to a network. These devices work together to ensure efficient communication and security within a network environment. A switch is a networking device operating at the OSI model's data link layer, layer 2. Its primary function is to connect multiple devices within a single local area network, LAN, and manage the traffic between them. Here's how a switch works. 1. MAC address learning. Switches demonstrate their intelligence by learning the MAC, media access control, addresses of devices connected to its ports. When a device sends a frame data packet to the switch promptly records the MAC address and the port through which the frame arrives. This valuable information is then stored in the switch's MAC address table. 2. MAC address table. The switch maintains a MAC address table, a forwarding or CIM table, that maps MAC addresses to the switch ports. This table is used to forward frames to the correct destination ports. 3. Frame forwarding. When a switch receives a frame, it checks the destination MAC address in its MAC address table. If the MAC address is found in the table, the switch forwards the frame only to the port where the destination device is connected, rather than to all ports like a hub would. 4. Broadcast and unknown unicast handling. If the destination MAC address is not found in the MAC address table, indicating an unknown unicast address, the switch forwards the frame to all ports except the one it was received on. This ensures that the frame reaches its intended destination. 5. Collision domain. Each port on a switch is its own collision domain. This means that devices connected to different ports can send and receive data simultaneously without interfering with each other, unlike in a hub where all devices share a single collision domain. 6. Switching and filtering. Switches use ASICs, application-specific integrated circuits, to perform high-speed switching and filtering of frames based on MAC addresses. This allows for efficient data transmission within the LAN. 7. VLAN support. Many switches support virtual LANs, VLANs, a powerful tool that allows network administrators to logically group devices into separate broadcast domains, enhancing security and optimizing network performance. In summary, switches are essential for creating efficient and secure LANs by managing and directing data traffic based on MAC addresses. They enable devices to communicate directly with each other within a network, reducing unnecessary network traffic and improving overall performance. Routers operate at the network layer, a layer 3 of the OSI model. They forward packets between networks using logical IP addresses. Each router maintains a routing table that contains information about known networks and the best paths to reach them. Routers are devices that direct data packets between networks, ensuring they reach their destination efficiently. Here's how routers route data. 1. Receiving packets. When a data packet arrives at a router, the router examines the packet's destination IP address. 2. Routing table lookup. The router consults its routing table, which contains information about network destinations and the paths to reach them. Each entry in the routing table includes destination network, the IP address range of the network. Next hop, the next router's IP address along the destination's path. Interface, the router interface through which the packet should be forwarded. Metric, a value that indicates the cost or distance to the destination, for example, hop count, bandwidth. 3. Choosing the best path, the router selects the best path to the destination based on the information in the routing table. If multiple paths exist, the router uses the one with the lowest metric. 4. Forwarding packets, the router forwards the packet to the next hop or the appropriate interface. A wireless access point, a device that effortlessly provides Wi-Fi connectivity to devices within its range, is a convenience and a necessity in our modern world. It connects to a wired router, switch, or hub via an Ethernet cable and emits a Wi-Fi signal to create a wireless network, eliminating the need for cumbersome wired connections. This means you can enjoy internet access on your devices without being tethered to a physical connection, enhancing your mobility and productivity. How wireless access points work. 1. Connection to wired network. A wireless access point is typically connected to a wired network infrastructure, such as a router or a switch, using an Ethernet cable. 2. Wi-Fi signal transmission. The access point broadcasts a Wi-Fi signal over a specific area, typically called the coverage area or wireless cell. 3. SSID, a network name. Each wireless access point has a service set identifier, SSID, essentially your wireless network's name. When you want to connect a device to the Wi-Fi network, you need to select this SSID. It's like finding the right door to enter a building. Once you've found the right SSID, you're one step closer to enjoying the benefits of wireless connectivity. 4. Security configuration. Access points are not just about providing Wi-Fi, they are also your first line of defense against unauthorized access. Equipped with robust security protocols such as WPA3 and WPAT2, they ensure the utmost safety of your wireless network. They may also employ encryption methods such as AES, Advanced Encryption Standard, which provides an additional layer of protection. You can trust your wireless network to keep your data safe and secure. 5. Client association. Wireless devices, such as laptops, smartphones, and tablets, can connect to the wireless network by selecting the SSID and entering the security key if required. 6. Data transfer. Once connected, data is transferred between the wireless devices and the wired network through the access point, which bridges the wireless and wired networks. 7. Coverage and range. The coverage area and range of a wireless access point depend on various factors, such as the access point's transmit power, environmental conditions, and any obstacles, walls, floors between the access point and the wireless devices. A wireless access point is a device that bridges the gap between a wired network and wireless devices, allowing them to connect to the internet or a local area network without the need for physical cables. It is essential in modern wireless networking, providing flexibility, mobility, and scalability in home and business environments. Network maintenance and troubleshooting are essential best practices to ensure computer networks' reliability, performance, and security. Maintenance involves regular tasks such as updating firmware, monitoring network performance, and managing network configurations to prevent issues and optimize performance. Troubleshooting, on the other hand, involves diagnosing and resolving network problems when they occur, such as connectivity issues, slow network speeds, or security breaches. It requires a systematic approach to identify the root cause of the issue and implement corrective actions, often involving network monitoring tools, diagnostic commands, and knowledge of networking protocols and hardware. Effective maintenance and troubleshooting practices help minimize downtime, improve network efficiency, and enhance overall network security. Network troubleshooting involves a systematic approach to identifying, diagnosing, and resolving issues that affect network performance, connectivity, or security. Here are some basics of network troubleshooting. 1. Identify the problem. This could be a complete loss of connectivity, slow performance, or specific application issues. This logical first step will guide you in the right direction. 2. Gather information. Collect relevant information such as IP addresses, error messages, recent changes, and affected devices. 3. Check physical connections. Ensure all cables are securely connected and devices are powered on. 4. Verify IP configuration. Check IP settings, subnet masks, and gateway settings to ensure they are correct. 5. Ping tests. Use ping to test connectivity to other devices on the network, including routers, switches, and other hosts. 6. Check DNS settings. Verify DNS settings to ensure proper name resolution. 7. Traceroute. Use traceroute to trace the path packets take from your device to a destination, identifying where issues may occur. 8. Check firewall and security settings. Ensure firewalls and security settings are not blocking necessary traffic. 9. Review logs. Check network device logs, routers, switches, and system logs, servers, computers, for error messages or indications of problems. 10. Network monitoring tools. Use tools like Wireshark for packet analysis, SNMP monitoring tools for network device status, and bandwidth monitoring tools to identify congestion. 11. Update firmware and drivers. Ensure network devices have the latest firmware updates and drivers. 12. Consult documentation. Review network diagrams, configurations, and documentation to understand the network layout and expected behavior. 13. Test with known good configuration. If possible, compare the problematic device's configuration with a known good configuration. 14. Isolate the problem. Use the process of elimination to isolate the issue to a specific device, segment of the network, or application. 15. Implement solutions. Based on your findings, implement solutions such as adjusting configurations, replacing faulty hardware, or updating software. 16. Document solutions. Document the issue, steps taken, and the solution implemented for future reference. 17. Monitor and test. After implementing a solution, monitor the network to ensure the issue is resolved and perform additional tests to confirm. Network troubleshooting requires a methodical approach and understanding of networking concepts and tools. It often involves collaboration between network administrators, system administrators, and sometimes third-party support or vendors. As network administrators and technicians, your role in network repair and maintenance is crucial. It ensures the smooth operation of computer networks, a vital component of any organization's infrastructure. Here's an overview of what's involved. Network repair. 1. Identifying issues, hardware issues. Check physical components such as routers, switches, cables, and connectors for damage or wear. Software issues. Diagnose problems with network protocols, configuration errors, or software conflicts. 2. Troubleshooting steps. Testing connections. Verify that all devices are connected properly and functioning. Network testing tools. Use tools like ping, traceroute, and network analyzers to diagnose issues. Log analysis. Review logs for error messages that indicate problems. 3. Repairing or replacing components. Hardware replacement. Replace faulty hardware components like switches, routers, or cables. Software updates. Apply updates or patches to fix bugs or security vulnerabilities. 4. Documenting issues and solutions. Maintain records of network problems and their resolutions for future reference. Update network diagrams and documentation to reflect changes. For network maintenance. 1. Regular inspections. Check network equipment, cables and connections for wear and tear. Review network traffic patterns and usage to anticipate problems. 2. Performance monitoring. Monitor network performance metrics like latency, bandwidth usage, and packet loss. Use monitoring tools to detect and address performance issues proactively. 3. Security audits and updates. Regularly update firewall rules, antivirus software, and intrusion detection and prevention systems. Perform security audits to identify and fix vulnerabilities. 4. Backup and disaster recovery. Implement and test backup solutions for network data. Develop and update disaster recovery plans to ensure minimal downtime in case of a network failure. 5. Capacity planning. Evaluate current network capacity and plan for future growth. Upgrade network components as needed to handle increased demand. 7. Training and documentation. Provide training for IT staff on network maintenance procedures and best practices. Maintain up-to-date documentation on network configurations and procedures. Network repair and maintenance best practices. Proactive monitoring. Detect problems before they affect users. Regular backups. Ensure data can be recovered in case of a failure. Security updates. Keep software and systems updated to protect against threats. Documentation. Maintain accurate records and diagrams for easier troubleshooting. Focusing on repair and maintenance can help IT professionals ensure that networks remain operational, secure, and efficient. Network security best practices are guidelines and recommendations that help organizations protect their systems, networks, and data from cyber threats. Here are some key network security best practices. Strong passwords. Use complex, unique passwords for each account and change them regularly. Consider using a password manager to store and manage passwords securely. Multi-factor authentication. Enable multi-factor authentication wherever possible to add an extra layer of security. This typically requires a second verification form, such as a code sent to your phone. Regular software updates. Keep all software, including operating systems, applications, and security software, up to date to protect against vulnerabilities. Backup data regularly. Regularly back up important data and verify that the backups are working properly. Store backups securely, preferably off-site or in the cloud. 5. Employee training. Educate employees about network security best practices, including recognizing phishing attacks, using secure passwords, and reporting suspicious activity. 6. Access controls. Implement the principle of least privilege, ensuring that users have the minimum level of access necessary to perform their jobs. 7. Network security. Use firewalls, intrusion detection systems, and other security measures to protect your network from unauthorized access and attacks. 8. Secure configuration. Configure systems securely and disable unnecessary services and features that could be exploited by attackers. 9. Incident response plan. Develop and implement an incident response plan to quickly detect, respond to, and recover from network security incidents. 10. Data encryption. Encrypt sensitive data at rest and in transit to protect it from unauthorized access. 11. Patch management. Regularly apply security patches and updates to systems and software to protect against known vulnerabilities. 12. Mobile device security. Implement security measures on mobile devices, such as encryption, MFA, and remote wipe capabilities. 13. Vendor security. Ensure third-party vendors and partners adhere to network security best practices and standards. 14. Monitoring and logging. Monitor systems and networks for suspicious activity and maintain logs for auditing and investigation purposes. 15. Compliance. Stay compliant with relevant laws, regulations, and standards, such as GDPR, HIPAA, and PCI DSS, to protect data and avoid penalties. By following these network security best practices, organizations can strengthen their security posture and reduce the risk of cyber attacks. In this short video, Students were introduced to the foundational concepts for troubleshooting and maintaining computer networks. The lesson covered topics such as network components, routers, switches, and wireless access points, common network protocols to include TCP/IP, DNS, and DHCP, and basic network troubleshooting techniques, ping, traceroute, etc. Students also gained insights into network security principles, including firewall basics and access control. Overall, the lesson provided essential knowledge to equip IT helpdesk professionals with the skills to effectively support and troubleshoot network issues. Thank you for watching.